So let's put that there. Let's put this here. Let's put that there. Here. Right. So in this lecture, I'm going to finish off what we're doing for small step reduction for lambda calculus, and then we'll do some big step reduction for lambda calculus. Okay, so we've seen we have this rule which says, so small step, the judgment form is we just write S reduces to T. And we've seen that there's some basic rules that we've already seen. So for example, we've got the beta rule that we've been doing. So what's that? That's lambda x arrow T x. But with S, this reduces to T S. Okay, so that's the main rule. That's all the hard work. If you understand this and you can do this, you've done the intellectual effort. The rest is just, figuring out how to write your answers out in the style that we like. So that's the main thing to do. And we did a few reductions before, and you've done this in previous class, and you're fully aware of what's going on, so that's very good. Okay, but of course there's a few other rules that we sort of used previously, and I'm just going to give you them, and you'll see that they're all very trivial. So for example, if you have two numbers added together, well, they reduce to, guess what? Now this might seem trivial, but remember, this is actual addition, where you actually do the addition on the numbers, whereas this is the syntax. So this is a piece of syntax, and that's the actual result of doing the addition. And you can see that this is the syntax because you've got the brackets from the syntax. Okay, and also, well, what happens if we want to do this rule in the middle of some big term? Got some big term, and somewhere in the middle we find a redex. Well, we need rules to allow us to do that. So if we have f reduces to f prime, then f applied to a reduces to f prime applied to a. Similarly, if we have a reduces to a prime, then f of a reduces to f of a prime. And then if we have S reduces to S prime, then S plus T reduces to S prime plus T. If you have T reduces to T prime, then guess what? S plus T reduces to S plus T prime. I think I've got them all. One more rule. And if we have T reduces to T prime, then lambda x lambda T x reduces to lambda x T prime. Okay. So those are all the rules you need in total. 1, 2, 3, 4, 5, 6, 7. So now in the next coursework, in the exam, I'll give you a term and I'll say, do reductions. And we saw that how we do that informally in the class in the last lecture, but formally you build up these trees. So if you've got something reducing to something and the redex to the first part, well, you have to use this rule. And then how do you do this? This might be where the beta redex occurs. Or again, you might use another one of these context rules to get to the redex, which is actually somewhere buried in the middle of the term. Okay. So that's small step reductions. And all I want you to know is if I give you a term, that you can use the system to produce reductions. That's the sort of thing that you have to be able to do. So I want to do a few reductions myself, just to show you some of the things that you'll come up against. So, this is a Turing complete language. You can write any program you want in this language. It's very small, that's why it's very powerful. You can write everything in this tiny language. That's why people use it as the basis for a lot of languages. But you know that programs can go wrong, so obviously some of these reduction sequences can go wrong too. So I want to show you a few things too about what can go wrong. So one, reduction doesn't always terminate. So in other words, you can do a reduction, do a reduction, do a reduction, and you're hoping you'll get the results at the end. But sometimes you don't. Sometimes it just goes on forever. It's a bit like a while loop going on forever, I guess. So for example, if you have lambda x arrow x applied to x, so if you look at that term, you say, oh, this is a regex. So I've got a lambda abstraction applied to a term. I've got a lambda abstraction applied to a term. So I can do my reduction. So what do I get? I get the body of this. So this is my t. So this is t of x. If you like, this is s. So I get t of x, but I have to replace the x with s. So, well, this is x applied to x, but x gets replaced with this. So the first x gets replaced with this, and the second x gets replaced with this. So what do I get? The first x gets replaced with that. So I have lambda x arrow x x applied to the second x, which gets replaced with this. So that's lambda x arrow x x. And you see you've made no progress. So this reduces to itself, reduces to itself, reduces to itself, reduces to itself. You're never getting one of these values. Okay, and then the other thing I wanted to point out is reduction order matters. I should say this is not about the lambda calculus, this is about programming languages in general. Programs sometimes don't terminate, that's what this is saying. And also the order in which you do computation matters in all programming languages. We're just seeing how that manifests itself here. So let's have an example. Let's call that term omega. And I'll consider that term. So the rules I gave you allow you to do a reduction anywhere. So you could say, oh, there's a beta redex, there's a redex, so I can reduce that. So let's do it again. There's my t, which actually doesn't use x, and there's my s. So one thing this could do is it could reduce to t, which is 5, but omega replacing x, so that's just 5. Hooray, we've got an answer. Alternatively, what we could do is reduce here. We could say, oh, this is an application. If we look at one of the rules I wrote just now, this rule says, if I've got one term applied to another, well, I could reduce the a to make a reduction. So if I do that here, I could reduce this omega. So this could reduce to lambda x arrow 5 omega. Again, carrying on. So, reduction order matters. If you get the wrong, if you start reducing the wrong redexes, you'll never get an answer. That's just the way the world is. You have to remember that programming language is design and implementation. You know, there are pitfalls, there are problems, because when you can write all possible programs, you can write all sorts of errors as well, because they're programs. So these things can happen. There's no right answer, there's no wrong answer. You have to be aware of the problems and decide when you want to cope with them. And the problem is even more, it's greater than that. Right. So what you might say, what you could say is, actually, sorry, if you see a term like this, an application, never reduce this. Do this overall redex first, do the substitution, and later on reduce this term. That would prevent this happening. Don't reduce the A's when you've got FA. Reduce F to a lambda term, and then do the reduction. You could try that. But here's another problem that can occur. So if you try that one, so what happens? Well, what you could do is you could reduce this, the 2 plus 7. So this could go to lambda x, arrow x plus x, and you get 9. 2 plus 7, that reduces to 9 by one of the rules I gave you. And then you say, oh, there's a beta reduction. It's the lambda term applied to something. There's my t. There's my s. So then I get 9 plus 9 goes to 18. That's fine. Alternatively, I could say, oh, here's a term applied to something, a lambda term applied to something. So what I can do is I can reduce this. I can say, there's my t of x, there's my s. So this gets to x plus x, with the x replaced by 2 plus 7. So we get 2 plus 7 plus 2 plus 7. And then I could reduce one of them, 9 plus 2 plus 7, and then another one, plus 9 and 18. So the good news is, same answer. Bad news, this one took more work because we had redexes inside here, and when we replace it with x, if x occurs 1,000 times, then each of these redexes will be replicated 1,000 times. Here it was actually just 2. Was it? Left-hand side, duplicated work. So there's no general answer. If I say just do the beta redexes when you can, I could duplicate work. On the other hand, if I say let's not duplicate work, let's reduce the input first, then I can get all sorts, I can get infinite stuff happening here. I could do work here, which is not even required because the x isn't used. So a lot depends upon whether x is used in here. And there's no right answer because some terms we'll use the x inside here once, some terms will use them no times, some will use them many times. So, okay. Right. So, you'll get lots of practice about that. Oh dear. So, we did big step reduction for imp. Now we'll do a big step reduction for lambda calculus. So we're not trying to do a little bit of work, a little bit of more work, a little bit of more work, lots of small easy steps. We're trying to just go in one step for the answer. Right. So what are our values going to be? So remember, our judgment forms will be now t reduces to some value. And what are our values? Well, if you think about it, the lambda calculus, it has abstractions, applications, variables, numbers, additions, and numbers. So out of those, there'll be some of them will be values, and the values should be numbers so that first of all they could be lambda abstractions. Okay, so there's two sorts of values. Of course, numbers are values, but functions are values as well, lambda abstractions. And notice, sneaky point here, so in a lambda abstraction, the body can be anything. So the reason is because we don't want to reduce inside the function until we know, till some input comes along. Okay, so those are our values. And those are our judgment forms. So now, all we have to do is write a rule for each piece of syntax. Okay, so, right. I'm going to see if you can do this. So, these are our judgment forms. So we want to write one of these for every single type of term. And we know that terms come in various forms. Variables, numbers, additions, applications, and abstractions. So just like with imp, where we had one rule for each piece of syntax, we'll have one rule for each syntax inside the lambda calculus. So one of them is numbers. So, right. What should we do? Let's start in the corner. What do you reckon? If I've got a number, what should that reduce to?
A number?
Yeah. Any particular number?
The same number?
That's a great idea. So I gave you an easy one. So we're just going to go through all the different syntactic forms and write down when does a term reduce to a value. And if the term happened to be a number, bingo, we're in luck. Nothing to do. The number reduces to itself. We're done. Okay. Right. Here's another type of term in the lambda calculus. Additions. So what would an addition? How are we going to reduce an addition term? What do you reckon? Now that you're following this. No, you've already impressed me. I want to be impressed by everyone.
Same again.
Well, say this was the term 7 plus 2. Oh, in fact, no, let's say it was the term t was 7 plus 2, and s was 5.
Would you actually just do the addition?
Well, if this was a number, like this was 3 and this was 8, yeah, I could just do the addition. But maybe this is not 3. Maybe this has terms inside it already. This t could be a huge thing. Yeah. This was just a number, so this has got to be 5 or 8 or 9. So this can be a huge term. So maybe we might have to reduce that. What do you reckon?
The meaning of t plus the meaning of s?
Yes. So what should we formally write? You said the meaning of t. So let's work out what would we write for the meaning of t. We'll write a t up there to start with. Your turn next. Hello. What should you write next? So when you say the meaning of t, that's right intuitively, but because we want to be absolutely precise, I'm going to force everyone to write in these sorts of these judgment forms. Everything looks a bit like that. I can't write the meaning of t. I'm not writing those words. What should I write?
I'm a bit lost right now, to be honest.
Okay, that's fine. So, that's good you told me, because I can't help you if you don't tell me. So what we're doing is trying to say, when is a term reduced to a value? Right? So these terms, these are these big lambda terms you've seen. And these are values like numbers 7, 12, 15, or possibly these lambda abstractions. And this is how we say t reduces to something. So far, we'll try and say, what will t reduce plus s reduce to? Well, first of all, we should reduce t. So, what should we write down next?
So would you have the downwards arrow and then t
Exactly.
prime?
Yes. You would say, let's try and figure out what does t reduce to. Great. Okay, your turn. What should we write next? V, yes. Let's say t reduces to some value. So that's how we formally write the meaning of t. You were right in informal English, but doing this precisely because computers which implement this stuff can't read English. They need precise instructions, so we have to use this mathematical notation. So we're going to work out what t reduces to. And we've said maybe it reduces to v. Your turn next.
Evaluate what s.
Yep. So how would we write that formally? Very good.
So it's the same again, so like x reduces to some potential upper value.
Okay, so s reduces to something. Very good. What shall I write next?
Could be anything.
It could not be anything. It could be almost anything.
Okay.
There's one thing it can't, well, actually there's 3 or 4 things it can't be.
So could it just reduce like
B. It could be B, but we're trying to use suggestive variable names. So if I wrote B, that would be correct. But also, despite the fact this is mainly for machines, we also want to read it ourselves. So why don't we choose V prime to suggest it's another value? Because if I wrote B, I might think, maybe it's a Boolean. Erroneously, that would be my fault, but I might do it. So I'm going to write V prime. Okay, your turn?
That be v plus v prime.
Yeah, so this V is hopefully a number, this V prime is hopefully a number, so I can write V plus V prime, and again, this plus is the plus on integers, not the syntactic plus that's inside lambda terms. Great, you can do this. I could retire and just give you the notes. Fantastic. Right, so the good news is only 2 more to go, and then we're done, hooray! That's the nice thing about the lambda calculus, I've said it before, it's short. There's only a little bit of work to do. So now, we've done additions, we've done numbers, we've done additions, what's left? Let's do lambda abstractions. How am I going to write this? So I've got an arbitrary lambda term. Okay, where do we get to? Your turn.
Do you do?
So look at your values. So this is obviously I started with the easier ones, and obviously I was getting slightly more difficult. So that's not going to be a number. So it could well reduce to a lambda term. That could be the value. So is it a value already? If so, you've got no work to do. If it isn't a value, you have work to do. Do you think it's a value?
Yes.
Yes, with a bit of hesitation. Okay. Well, see here I said a value could be any lambda term, any variable, and any term here.
Yes.
So this matches that. So yes, with energy and determination and confidence. So just like with numbers, that's already a value. So there's nothing to do. Had I written for some reason value here, then this would not work because I can't guarantee that this t is a value. So I might have to reduce t. But since we're not doing that, that's fine. Very good. Right. So one last rule. So in lambda calculus, in all languages, all the work is done when you have something that requires input and you give it input. In the lambda calculus, that's application. So we're going to do the last rule now, and that requires a little bit more work. But not too much. And I'm very confident that you over there will be on top of your game. So let's have a term. Oops, that's a bit wonky. Oh, we don't need that. Let's just do that. I won't distract you with anything. So we've got this term, f applied to a, and we want to work out what the value is. So what should we do? Let's see, it's your turn next.
I'm not sure.
Okay, that's fine. Well, the way we do things is to look for redexes, beta reductions, isn't it? So, or even plus signs. And we can't see any beta reductions, we can't see any plus signs, so we can't do anything immediately. So maybe we should work on f. How does that sound? Try and reduce f. Just like when we did addition, we couldn't work immediately, we couldn't do addition immediately because this t could be a very big term, and this s could be a very big term. So we worked on t and we reduced it to a value, an actual number. And we reduced s from this very big term to an actual number, which we could add. And we've got a similar situation here. Here. We've got something applied to something else, and we don't really know what they are, so we need to work on them. So let's work on f. What do you think we could do?
So we need to find the meaning of it.
Exactly. Brilliant. We need to find the meaning of f. What should we formally write down to find the meaning of f? You've seen a few of these things before? Can you have a look at that?
Whenever it's like F and then the arrow.
Yeah. Let's work out what f reduces to. Very good. Now, what do you think it could reduce to? Well, it could reduce to an f prime, but an f prime is not a value. Remember, it's got to be a value. And if it was an f prime, it still wouldn't be a beta, it still wouldn't be a plus, so we couldn't really do anything with it. So that's a good guess, but I think we need to think a little bit more. So these are our sorts of values. The f could reduce to either a number or it could reduce to a lambda term. Now remember, this f is being applied to something. So I don't think we want to get a number, because a number, 7, can't take some input. So what we really want to do is take our f and reduce it to a lambda term to create this reduction. So your turn next. What should we write?
V?
V. Well, V would be any value, but I don't want it to be any value. I really want it to be a lambda abstraction.
So it will be the lambda x ROT thing.
Yes. It would be the lambda x arrow t thing. So this says, let's find the meaning of f, and let's make sure it's a lambda term. I could have written f reduces to v, but then later on, what do I do with this v? I don't know anything about it. It could be 7. And what is 7 applied to a? It doesn't make sense. So I'm being more restrictive. I'm saying f has a meaning, and it must be a lambda term. Great. Okay. What's next?
Do you think A up?
Yes, let's do something about a. And I'm going to say, let's substitute a for x. Yeah? Now, I'm going to come back to this because I just made a choice. In a moment, we might do something else. But that's a possibility. Okay, it's a possibility. So this is what happens. You remember earlier on, I was saying, if you've got a lambda term applied to something, should you do the reduction immediately, or should you work on the something? And there are choices. If you work on the something, it could go on forever. On the other hand, if you don't work on the something, you could be copying work. So there are choices. Here, we're choosing not to work on the a. We're just going to put the a inside the term. So the danger is, if this x occurs several times in t, a will now occur several times in t. And any work inside a, any work inside a will now be duplicated. So that's the danger of this rule. The advantage is that if a will just run forever and t does not use a, the advantage is we won't fall into that problem. So that's what we're going to do here. Right, your turn next.
So it should evaluate
Evaluate to.
either a number.
Well, you know what? At this point, I don't really care. Here I needed f to be a lambda abstraction to do this reduction. But here, actually, anything will do. So, of course, I only give you 5 seconds to think about it, which is unfair of me, and I'm sorry about that. Yeah, you could wonder about it, but a little bit of time you'll realise anything will do, so any value. Finish it off then, your turn. What should I write here? V. Yeah. There we go. So, that's big step reduction for lambda calculus in... Will I fit it on? Oh no. There we go. That's all you need to know. Very small, much better than imp if you ask me. Very precise. But notice, here, we chose to not reduce A first. So this is called, and it's got a technical term, I want to tell you what it's called call by name. Sorry, thank you. It's call by name reduction. It's because we just give the name of A, we don't do any work on it. Had I written but the same thing, let's reduce F. And then let's see if A will reduce to some value. And then let's do T applied to V, reduces to V prime. F, A reduces to V prime. If I've written this, you see now, I would not do the substitution immediately. I would not put A into the body of the term. I would instead reduce A as much as I can. And when A is a value, then I put it into the term, and then I carry on computing to get the overall result. So this is called call by value. It's called call by value because I call the function on the value of its input. And like I said, neither call by name nor call by value are better than the other. Call by value is good if X occurs inside T many times because we do the reductions in A once. So then when we put it into T, we don't duplicate that work. Call by name is good when, if we try to reduce A, we might be doing work we don't need because X does not occur in T. Okay, so you need to be aware of both of those. Okay, nearly finished. Right, so let's have a look. So notice some things. So, of course, every term does not reduce to a value. We saw that term omega at the beginning. It just keeps on reducing. If you try and do it in small step semantics, you see it reduces to itself and reduces to itself, reduces to itself. If you try to do it in big step semantics, you'd find that, well, this would be lambda x, xx applied to lambda x, xx. F, that already is a lambda term, so that'd be done. And then you'd have the term with lambda xx for x. So this would be the same as this. And so you'd see, in order to reduce this, I have to reduce the same thing. So you wouldn't get anywhere, you wouldn't make any progress. So not all reduction sequences terminate. With the small step semantics, I showed you there were different ways to reduce the same term. Some had greater length than others. Here, notice, this is deterministic. There's only one thing you can ever do. Now, those of you who like following rules, that's great, because there's no creativity. If I give you a term and say, reduce this term for me, you don't need to be creative. You just follow the rules. If it's an application, use this rule. If it's a lambda abstraction, use that rule. If it's a number, use that rule. If it's an addition, use that rule. So you just can do what you're told, and everything will work out fine. So that's what deterministic means. Right. We still have to do substitution. This big process of replacing the x's in T by A, or the x's in T by V. We still have to do that. We have to worry about variable capture. And finally, yes, so in call by name, as I've said, we only reduce A once it's inside T. That's a win if X is not in T. Otherwise, this is better. Okay, now I said I'd give you something to do, so let me do that. So here's your homework for the next lecture. So write a big step reduction in natural deduction tree style for, let's have a look, lambda x dot x plus 3 applied to okay, there you go. And I'll tell you what you should get. So you should get, let's say, use call by name reduction. And the answer is, let's see if I can do it in my head quickly. So so let's see. So this is a, oh, what is this? This is this applied to this. So that's this. So there's a lambda term applied to 5, so I could replace x with 5, but that x is this x is this x, so so that won't happen. So instead I will get, let's call that 4. Right, so when I put this in here, I'll get 4 plus 2 plus 3, which is 4 plus 2 is 6, and 3 is 9, so I'll have lambda x dot lambda x dot 9 applied to 5, so I think the answer is 9. Okay, is that clear? Ah, sorry.
Where are you getting 4 from?
4 is a number. So remember, inside my lambda calculus, I've got. So I didn't mean to be. Sorry, that wasn't meant to be put down. The syntactic categories of lambda calculus are variables, applications, lambda abstractions, numbers inside brackets. Sorry, I've got my brackets there. Okay, any other questions?